Usually when we talk about logistics or global trade, we're talking about efficiency in a very boring geometrical sense.
Right. It's an optimization problem.
It is. How many square boxes can you stack on a rectangular ship?
Yeah.
It's just Tetris on a massive scale.
A spreadsheet exercise, basically.
Exactly. But today, we are looking at a sector of global trade where that efficiency problem is actually a terrifying physics problem.
Okay.
We're looking at a stack of documents, and the core one is a cargo operating manual for an LNG carrier, liquefied natural gas.
Yes.
And what struck me immediately is that this doesn't read like a shipping manifest. It reads like a survival guide for a very specific, very hostile environment.
That is a fair assessment. I mean, I've read a lot of technical manuals, and LNG manuals they're unique. They're essentially dealing with a substance that just wants to be something else.
What do you mean?
You're taking a gas, you're shrinking it, and you're trying to keep it in a state that nature really, really opposes.
Okay, so let's start with that shrinking aspect, because that's the statistic that just jumps off the page. The 600-to-1 ratio.
That is the magic number. It is the entire economic justification for this industry.
Right.
If you want to move natural gas methane across an ocean, you just can't do it as a gas. It takes up way too much space. You'd need a fleet of ships the size of Manhattan just to power a small city.
So you have to dense it?
You have to liquefy it.
Yeah.
When you cool natural gas down to, minus 162 degrees Celsius?
That's minus 260 Fahrenheit.
Right. It undergoes a phase change. It turns into a liquid. And in that process, its volume just collapses. It shrinks by a factor of 600.
So if I had a single standard milk jug of LNG and I let it warm up,
Yep.
it would expand to fill 600 of those milk jugs with gas.
Exactly. Or think of it this way. One LNG carrier is effectively transporting 600 ships worth of energy.
Provided they can keep it cold.
And that's the catch. It's extreme physics. You are transporting a volatile, flammable fuel at cryogenic temperatures, often through the tropics.
The temperature difference must be enormous.
It is. Between the cargo and the seawater outside the hull, you're looking at nearly 200 degrees Celsius.
Which brings us to the beast itself. The manual spends a lot of time defining what LNG actually is. And I think I had a misconception here. I just assumed natural gas meant methane.
That's the common assumption. And it is primarily methane, maybe 85% to 95%. But the manual is very careful to define it as a mixture. It's a cocktail, a soup.
So what else is in there?
You have methane, which is the lightest, but you also have ethane, propane, butane, even pentane mixed in, plus a little bit of nitrogen.
Why does that distinction matter so much? Why can't we just treat it as gas?
Because it's not a stable compound. Since it's a mixture, all those different hydrocarbons have different boiling points.
Okay.
Methane boils at minus 161.5 Celsius, but propane boils at minus 42. They behave differently when they warm up.
And this leads to this phenomenon the manual calls boil off.
Right. No matter how good your insulation is, and these ships are basically massive double-hulled thermos flasks, you can't stop the laws of thermodynamics.
Heat is going to leak in.
Heat will leak in. The ocean is effectively a hot plate heating the bottom of the ship. The sun is heating the deck.
So the cargo is constantly boiling the whole trip.
It is. The liquid is always simmering. And this goes back to the mixture issue, because methane and nitrogen are the lightest components.
They boil off first?
They boil off first, they escape the liquid and turn into vapor.
So you're essentially performing fractional distillation in the middle of the Pacific Ocean.
Precisely. You're distilling the cargo. As the voyage progresses, you're losing the lighter stuff, the methane. That means the liquid left behind is getting richer.
Richer with what?
A higher percentage of ethane and propane. So the LNG load in Qatar is literally chemically different from the LNG you offload in Tokyo 3 weeks later.
It's denser. Burns hotter, I assume.
It does. And the crew has to know that their cargo is aging during the trip.
Now, the manual says this boil-off isn't just waste. They need it, right?
It's a critical part of the safety system. If you just seal the tank tight, the pressure would build up from the boiling until the tank ruptured. You have to let the gas escape.
And they use that gas to power the ship.
Most modern carriers do, yeah. They capture that boil-off gas and feed it into the ship's engines. The ship is powered by its own cargo, but there's a very delicate balance here with the pressure.
This is that equilibrium thing the manual talks about.
Yeah, this is where the physics gets a little tricky. If you pull that vapor out of the tank too fast, say the ship's engines need more fuel.
So the pressure inside the tank drops.
Right. And basic physics says when pressure drops, the boiling point drops.
So the liquid suddenly thinks it's hotter than it is.
Exactly. It suddenly finds itself superheated relative to the new lower pressure, so it flashes. It boils violently like a pot boiling over on the stove to create more vapor and restore that pressure balance.
So the crew is constantly walking this tightrope. Pull too much gas, the cargo goes unstable. Don't pull enough, the pressure gets too high.
It's a dynamic system. You're not just storing a liquid, you're managing a phase change for weeks at a time.
Let's move to the safety side. The biggest risk with gas is obviously fire. But the manual presents this idea of the flammability triangle. It's not as simple as gas plus spark equals boom.
No, not at all. Methane is actually a pretty picky fuel. It doesn't just burn whenever, it has a specific flammable range.
And the manual says that's what, 5.3% to 14%?
Correct. That's the window. If you have a mixture of air and the methane concentration is below 5.3%, it's too lean, not enough fuel.
And above 14%.
It's too rich, too much fuel, not enough oxygen to burn it.
So just theoretically, if I was standing inside a cargo tank that was 100% methane vapor and I lit a match,
the match would just fizzle out. It needs oxygen to burn. There's zero oxygen in there. It's chemically impossible for a fire to start.
that feels incredibly counterintuitive.
It is. But here's the operational nightmare the manual highlights. When a ship comes out of dry dock, the tanks are full of air.
Normal air, 21% oxygen.
Exactly. And you need to fill those tanks with methane. To get from 0% methane to 100% methane, you have to pass through that 5.3 to 14% range.
You have to cross the explosive envelope.
If you just pumped gas in, there would be a period of time where the entire tank was a massive bomb, just waiting for a static spark.
So they have to cheat the triangle. They use a process called inerting.
Exactly. Before they introduce any methane, they purge the tank with an inert gas, usually nitrogen. They push all the regular air out until the oxygen level in the tank is below 2%.
So now you have a tank that's basically full of nitrogen.
Right. Now, if you look at that flammability diagram, because the oxygen is so low, that flammable range just doesn't exist anymore. The triangle shrinks to nothing.
So you can add as much methane as you want.
And the mixture will never become flammable because there isn't enough oxygen to support the reaction. You move the mixture along a line on the graph that completely bypasses the danger zone.
They move tangentially to the risk. That is such a cool concept. Safety isn't about vigilance, it's about physics.
It's the ultimate engineering control. If the chemistry says no, an accident can't happen.
That's only while the beast is in the cage. The manual gets really descriptive about what happens if the LNG gets out. The section on spills and vapor clouds.
This is the nightmare scenario.
Yeah, I think people picture an oil spill. It floats, it's messy. But LNG is cryogenic.
You have to remember the temperature difference. To the LNG, the ocean isn't cold water, it's magma. The water is 180 degrees hotter than the liquid gas.
So if you spill LNG on the water,
it explodes into vapor, it boils instantaneously and violently. The manual says it spreads over an indefinitely large area.
And interestingly, it says no ice forms. I would have thought dumping something that cold on the ocean would create an iceberg.
You'd think so, but the boiling is so vigorous it prevents a coherent ice sheet from forming. It's a churning, bubbling cauldron. But there is a specific phenomenon mentioned, the flameless explosion.
Yeah, that sounded like a sci-fi term. Rapid phase transition, or RPT?
RPT. This happens when the liquid methane hits the water, and for a fraction of a second, the layer touching the water superheats. It gets hotter than its boiling point, but stays liquid, and then it instantaneously vaporizes.
So it's a physical blast, not a chemical one.
It's a shockwave. There is no fire. It's just the mechanical energy of that 600 to 1 expansion happening in a microsecond. It can release enough energy to damage the ship's hull plates without a single flame.
And the manual mentions this is more likely with aged cargo, the richer stuff.
Yes. The mixture with more ethane and propane is much more prone to these flameless explosions.
Now let's talk about the cloud that forms. My assumption with natural gas is that it rises. It just floats away.
Standard methane gas at room temperature, yes, it's lighter than air, but cold methane vapor is a different beast entirely. Density depends on temperature. At minus 160 degrees, methane vapor is significantly denser than air. So initially, the cloud doesn't rise.
Sinks.
It sinks, it hugs the surface, it flows along the deck like a heavy fog, or it crawls across the water.
That is terrifying for a crew member. You can't just climb a ladder to get above it.
No, it's right there at your feet. The manual describes it as long, thin, and cigar-shaped. It flows downwind, staying low.
And it only rises once it warms up.
Only once the gas gets warmer than about minus 100 Celsius, then it finally becomes buoyant and starts to lift off.
And there's a practical tip in the manual about this. It says, the white cloud is not the gas.
That is a crucial distinction. Natural gas is invisible. The white cloud you see is just water vapor from the air condensing because it's so cold, it's just fog.
But they say to treat the fog as the danger zone.
It's a safe rule of thumb. The actual flammable gas envelope usually sits inside that visible cloud. If you're in the white fog, you're almost certainly standing in a flammable atmosphere.
Let's shift to materials. Because it's not just dangerous to people, this stuff is dangerous to the ship itself. We talked about that Terminator effect.
Yes, the ductile to brittle transition. It's very real.
The manual warns that standard ship steel, the stuff the hull is made of, cannot touch the cargo.
Normal mild steel is a fantastic material. It's strong, it's ductile, it can bend with the waves, but that property relies on temperature. If you cool mild steel below about minus 30 Celsius, its crystal structure changes. It locks up.
It becomes like glass.
Essentially, it loses its ability to deform. If you spilled LNG onto a standard steel deck, the steel would contract rapidly and just shatter, brittle fracture. You could literally crack the hull of the ship open.
So the tanks themselves must be made of special stuff.
They have to be. They use stainless steel, aluminum alloys, or a special nickel iron alloy called Invar. These materials stay ductile even at cryogenic temperatures.
But the rest of the ship is normal steel, so if you have a spill,
you have to protect the hull. That's why you see stainless steel drip trays under all the pipes. And during loading, they often run a water curtain.
What's that? Waterfall down the side of the ship.
Basically, yeah. It's not to wash away gas. It's a heat shield. The water warms the steel hull and prevents the cryogenic liquid from making direct contact. It's a thermal buffer.
This leads to the rule I found the most counterintuitive in the entire document. It's in the emergency procedures. It screams. If you have an LNG spill in a drip tray, do not spray water on it.
This goes against every instinct a firefighter has. You see a problem, you apply water. But here, water is not a coolant. Water is a massive heat source.
Because relative to the LNG, the water is boiling hot.
Exactly. If you spray a fire hose into a pool of LNG, you are rapidly transferring heat into that liquid. You will make it boil faster.
So you're just making the dangerous cloud bigger.
You're feeding the beast, you're expanding the vapor cloud, or if it's on fire, you're increasing the intensity of the flame. The manual is clear. You can spray water on the surrounding structures to keep them cool. Never spray the liquid itself.
That just requires a complete rewiring of your brain. Hot is cold, water is fuel, air is the enemy.
It's a topsy-turvy world.
Let's touch on the silent killers. We've talked about fire and ice, but the health hazard section emphasizes something quieter: asphyxiation.
Right. Methane isn't a poison, not like chlorine. It's an inert asphyxiant.
Yeah. It just pushes the air away.
It displaces oxygen. And the danger is that the human body isn't programmed to detect a lack of oxygen. Our suffocation alarm is actually triggered by a buildup of carbon dioxide in our blood.
Not by a lack of oxygen.
No. So if you walk into a room of pure methane, you can breathe it in and out easily. Your body clears the CO2 so you don't feel like you're choking. You don't gasp, you just fade out. You get dizzy, and then you switch off.
That is terrifying.
It is. And the manual flags nitrogen as a huge culprit here, too, because they use so much of it for inerting. Nitrogen is odorless, colorless, and tasteless. It gives zero warning.
And the inert gas generated by the ship isn't pure nitrogen, is it?
No, that's generated by burning diesel or gas in a controlled way, so that gas does contain nasty stuff. Carbon monoxide, nitrogen oxide, so you have the asphyxiation risk, plus toxic poisoning.
Finally, I want to talk about how they detect this stuff. There's a technological gotcha in the manual about gas sensors that I found really interesting.
This is a detail that saves lives. Most standard gas detectors are catalytic.
How do they work?
They have a tiny bead inside. When combustible gas hits the bead, it actually burns on the surface. That burning creates heat, and the sensor measures the temperature change to tell you how much gas is there.
Okay, so it needs a mini fire inside the sensor to work, but to have a fire, you need oxygen.
Exactly.
And we just established the tanks are inerted. There is no oxygen.
Precisely. So if you stick a standard catalytic sensor into a tank full of methane and nitrogen, it will read 0.
Not because there's no methane, but because the sensor itself is suffocating.
It can't see the gas because it can't burn it. It's a fatal false negative. You could be in an explosive atmosphere and your meter says you're safe.
So what do they use?
You have to use infrared sensors. They shoot a beam of light through the gas and measure how much gets absorbed by the hydrocarbon molecules. They don't need oxygen.
It's just another layer of complexity. The right steel, the right physics, the right atmosphere, even the right sensor technology.
That's the nature of this industry. We're taking a fuel that is chemically very clean. It doesn't pollute water because it just evaporates. But we transport it using a process that is physically incredibly aggressive.
It really puts into perspective what's happening on those ships you see on the horizon. They look so peaceful, but inside it's this constant battle against the boil-off, managing pressure, inerting tanks.
It's a high-wire act. You're managing a fluid that wants to expand 600 times in a liquid state that shatters steel and constantly chemically engineering the atmosphere to prevent it from exploding.
It gives you a new appreciation for the magic trick we started with.
Absolutely. It's a marvel of modern logistics.
So what's the big takeaway here? For me, it's that concept of inerting. The idea that safety isn't just about vigilance. It's about changing the environment so that disaster is physically impossible.
It's the ultimate engineering control. Don't rely on luck. Rely on the phase diagram.
I want to leave you with a thought about that flammability diagram. We usually think of safety as a barrier, a wall we build. But in this case, safety is a path. It's a narrow channel you have to navigate between two catastrophic zones. So next time you boil a kettle of water on a gas stove, just remember the invisible geometry and the cryogenic engineering required to get that one molecule from the ground across an ocean and into your kitchen without ever crossing that red line.
Well said.
Thanks for joining us on this deep dive into the freezing cold world of LNG.
A pleasure to be here.
Stay curious, and we'll see you on the next one.